Consider how electron exhibits the same behavior as the same poles on a magnet would if they came into contact. As the negatively charged electrons fill orbitals, they first try to get as far as possible for each other before having to pair up. According to the first rule, electrons always enter an empty orbital before they pair up. Electrons are negatively charged, and as a result, they repel each other. Electrons tend to minimize repulsion with occupying their own orbitals, rather than sharing an orbital with another electron. And for the second rule, unpaired electrons in singly occupied orbitals have the same spins. Technically speaking, the first electron in a sublevel would be either spin up or spin down. Once the spin of the first electron in a sublevel is chosen, the spins of all the other electrons in the sublevel depend on that first spin. Scientists typically draw the first electron and any other unpaired electron in an orbital as spin up. And these are the electron configuration of these elements and the number of the valence electron. And the last one is octet's rule. The octet's rule dedicates that atoms are most stable when their valence shields are filled with 8 electrons. It is based on the observation that the atoms of the main group elements have a tendency to participate in chemical bonding in such a way that each atom of the resulting molecule has 8 electrons in the valence shield. The octet rule is only applicable to the main group elements. The molecule of halogens, oxygen, and nitrogen and carbon are known to obey this octet rule. In general, the elements that obey this rule include the S-block elements and the P-block elements. The octet rule can be observed in the bonding between the carbon and oxygen atoms in a carbon dioxide molecule, like this. Observing from this picture, we can see that both the oxygen atoms and the carbon atom are octet configuration in the carbon dioxide molecule. Observing that noble gases were chemically inserted, we can see that octet's rule was based on the tendency of atoms to assume the most stable states possible.
为什么4S 在3D 的前面？
因为4S 它是那个有2个那个
你说那个鬼域吗？
好像是
那个
然后那个4P 有6个，就是沿着这条线就是画下来。照理来说是应该按照是那个号码在走嘛。可是就是到这里，就是有时候它就是跟着那个轨，因为它可能能量比较高。
比较稳定嘛。
对。
So Hardy asked why the orbital 4s has to be filled before 3D. That's what this Aufbau principle explained. Charlie was explaining these ML things. If you look at the figure, it will be clearer because the text is quite complicated. But if you look at the left figure, that's usually how we explain the Aufbau principle. It's not really like it follows SPD regularly. Instead, you need to follow the red line at the left figure. 4S has lower level than 3D, so it has to be filled first.
可以解释一下为什么第3周期以后的元素它们可能可以超过巴玉体规则？
就是你看，像 PCl5，它就产生了5个键结，5乘2就是10，所以它就已经违反这个巴玉体的规则，因为巴玉体就是8个电子。
Steve asked why there are some compounds disobeying the octet rule. But in fact, this is not part of my question, because if you want to talk about exceptions, that would be too much for you. And for the mineral chemistry, all you need to know is octet. And Tiffany said, Neon has a valence shell electron number of 6, while Charlie has 8. Which one is correct? Of course, 8 is correct. Neon is one of the inert gases. Why they are inert? They obey octet rule. That means their valence shell electron numbers are all 8. Therefore, they are satisfied. Because they are satisfied, they don't react with others. Here, we actually have some error. I don't know how many of you have seen iron 8+. What are the typical charge of iron? We will discuss this later.
First, I'm going to talk about what coordination number is. In a molecule or crystal, many atoms bonded together. The number of how many atoms or ions bonded with an atom in the center is called the coordination number. The number is how many number are there atoms bonded with the single one. For example, like if this is a central atom and there are 2 atoms bonded together, then its coordination number would be 2. If this is a central atoms and 3 atoms bonded with it, then the coordination number would be 3. The Pauline's rule 1 tells us that there are some relationship between the coordination number and the ratio of cation and anion radii. So in this graph here, we divided the cation's radius by anion. So there are some ratios like smaller than 0.15 or 0.15 between 0.22. We can use them to look at what their coordination number is, so we can generally know what their structure would be like. For the Pauline's rule 2, that tells us that we can know the strength of each bond by dividing the electrostatic valence by its coordination number. The charge of an ion must be equal to the total amount of the charge of all bonds. Also, we can analyze molecules by rule 1 and 2 together. Titanium oxide as example. By calculating the ratio of titanium and oxygen, we can tell that the coordination number is 6. So that means 4/6 charge divided to each bond. 4/6 is equal to 2/3. 2/3 has to times 3 to be equal to the valence of oxygen, which is 2. So in conclusion, the oxygen will have a coordination number of 3. So that means titanium will have 6 bonds and oxygen will have 3 bonds. We can generally know what the molecule will be like by applying the Pauline's rule. Next is isodesmic. Isodesmic means the bonds that have same electrostatic valency. That means all the bonds have the same length as each other's. Graphite would be an example of isodesmic. The opposite of isodesmic is called anisodesmic. The definition of anisodesmic objects have different electrostatic valency, so their structure would be stronger by rule number 2. An example would be diamond. The structure of silicate minerals are usually mesodesmic. That means the bonds of cation and anion are half of other charges of ion, and that usually makes the structure of silicate minerals strong.
Is there a link between the number you write and on the figure when there is like Ti 4+ or O 2-?
I think because the coordination number of titanium is 6 and its valence is 4, so we have to make it 4/6.
The value here. The name of this number is the strength of the bond, which in short you can call them bond strength. And what's the definition of bond strength?
Dividing the valence by its coordination number.
How do you determine its coordination number? Can you explain that again?
To calculate the ratio of cation and anion radius.
What is mesodesmic?
Cation anion bond strength equal exactly half the charge on the anions.
But that sounds like isodesmic.
它的静电键强度会是氧原子的一半。
Gary said the bond strength between oxygen to silica or oxygen to another element It's the same. Is oxygen the cation or the anion?
Yeah, I guess it's anion.
Right. Here you almost write the correct answer. The bond strength between this combination, they are always half of the charge of the anion. This is particularly important because this explains the behavior of silicate, which will be our major role today. Mineral chemistry. This part is probably one of the most chemical lecture of this course. The first part will be a brief review of our orbitals because today we will talk a lot about orbitals, but that was already your assignment, so I will just go through it very quickly. This is how we usually think of orbital, but this is actually wrong. In fact, orbital is a concept of probability, the chance that the electron occur in a certain space around the nucleus. From your chemistry lecture, you know there are several kinds of orbital, SPD. Each of them have different kinds of configuration, different numbers of configuration. This means their valence shell. On the periodic table, elements with different valence shell orbital configuration, they occupy different block. This is already reviewed in your assignment. We don't want to talk about physics. We just want you to refresh your idea about electron orbital so that you know how to fill in the orbital and you also know how to count the valence shell, how to draw octet. This is the Aufbau principle. You need to fill in the shell or electron orbitals in this order. And this is Pauli exclusion principle. For each orbital, you can have up spin and down spin. Valence shell means the outermost shell. In this case, it means the S shell. Shell is defined by the number. Lastly, the third rule is Hund's rule. In my chemistry training, there would be some tests where you need to draw the spin of electrons. Therefore, you need to know the Hund's rule. You need to draw these two up spin first instead of one up spin and one down spin. This is not that important because we will be mainly focusing on the configuration that is in the table of your assignment. That is this table. If there is one element you want to know its electron configuration, what would you do? The answer is very easy. You search that element in Wikipedia. Here, this is its electron configuration. However, in Wikipedia, it would be very much simplified. It will usually write this. What does that mean? It means before this, you need to fill in the electron configuration of argon. And here, in the case of argon, it writes neon. And then in the case of neon, it writes helium. So they always cite the previous inner gas. That's how Wikipedia write their electron configuration. So you can check on Wikipedia to know if your answer is correct. And then, of course, you need some common sense to know that we don't see iron 8. From scandium to zinc, these are the transition metal. There are complications here. For the early transition metal, 4s orbital will be filled first. Early means 21 to 25. But for late transition metal, of course, we fill the 4s2 first. However, at this time, 4s2 will act like the real valence shell. This complication comes from the fact that these two orbital 4s and 3d, they have rather comparable energy level. And the energy level may change depending on how many electrons are filled into this orbital. So you see sometimes one is higher, sometimes the other is higher. At the end of the transition metal, it follows the regular rule. Again, that's arsenic. Now we talk about bonds. We know there are several chemical bonds, but today we will focusing on two bonds. One is ionic, the other is covalent. This is an ionic bond, sodium chloride, salt. It basically follows electrostatic attraction. This is the electron configuration of sodium, and this is the configuration for chlorine. This is the valence shell. This is the valence shell. In nature, you barely see this, or you barely see this. you often see these two. So that means this guy gives one extra electron to this one. So sodium plus will end up with 8 electrons here. And chlorine will also end up with 8 electrons here. Then they will match octet, and then they will be stable. And the other is covalent bond. Covalent bond is doing this by sharing electrons. We use this as example. That means sharing electrons. Alone, their valence shell don't follow octet rule, so they are not as stable as this one. This one will be stable because each of them will have 8 electrons. This is a very simple example. Later, we will have very complicated examples for each. That's for general chemistry. Let's now go to minerals, the focus today. What is the definition of minerals?
是透过地质作用自然形成的，然后通常都是无机的。
Produced by natural process and inorganic. That's all. Then maybe ice is also a mineral.
还要看它的那个晶体结构。
Very good. There has to be crystal structure. Okay, naturally occurring inorganic solid ordered atomic structure that usually means crystal. Which of the following is not a mineral? Is quartz a mineral? Yes? Okay, glass? Why not? There's also naturally produced glass like volcanic glass. No, they are not mineral because they don't have crystal structure. Is diamond a mineral? Graphite? Yes. Is calcite mineral?
Yes.
Carbonate?
Maybe. Yes. No.
Carbonate is not a mineral. Carbonate is rock. So you need to differentiate mineral and rock. Muscovite? Yes. Okay. Granite? No. Granite is rock. Gold? Yes. I don't know, after this QA, will you have a better idea what is a mineral and what is not a mineral? Previously, I told you that in many textbooks it says inorganic solid. In reality, there is also organic mineral, like this one. This one has an organic structure like this. It's the crystal of PAH. Organic minerals are rare, but they exist. Therefore, in the future, I will not say minerals are all inorganic. They are also organic minerals. Classification of mineral. Scientists several centuries ago, they have debated how should they classify mineral. At the end, they decided that they should classify mineral according to the type of anion or anionic complex. That's what mineralogists would do. Therefore, in the future, if you see names like these, they means a group of minerals. And the group of minerals are named after its anion, not cation. We will focusing on silicate, but in this department, I know someone may be working on carbonate, like foraminifera. They are biogenic carbonates. So these are the mineral class we usually deal with. And then carbonates, when you see a name like this, they are either a kind of rock or a class of mineral. But it doesn't really refer to a specific mineral. So how do you tell if this name corresponds to a specific mineral? It's very easy. This compound must have a chemical formula. Every mineral has a chemical formula like this. These are very specific. For most students, the most painstaking part is the ordered atomic structure. We are talking about crystal, highly ordered atomic structure. But you need to be aware that crystal can be produced artificially. But minerals are all natural products, so you have to make this distinction. What do we need in order to have crystal? First, atoms, they must fit together in terms of their size and charge. They have to be able to pack together. They shouldn't be like a randomly spreading. Then they don't make crystal. So they need to fit together. This part was also your assignment for the B student. And the second is their structure has to be symmetrical. Now I'm packing like I have Lego, but these Lego, they are balls. However, after I pack a unit like this, which may contain 15 balls, for example, I need to be able to repeat this unit in this direction, in this direction, in this direction. I need to be able to repeat this basic unit in 3 dimensions. That makes mineral. Their spatial arrangement has to be symmetrical so that they can repeat themselves endlessly. So we need to talk about atomic structure. And then this basic unit, they are so-called unit cell. They are a different concept comparing to polyhedron in your assignment. I will tell you later. First, we need to talk about ionic radius, which is the radius of the ion. Is it bigger or smaller? Apparently, this depends on the electron. Because nucleus, they are usually very small. So usually this depends on the electron. Which one has larger ionic radius? Cation or anion? Lithium, sodium, potassium, rubidium. Potassium, magnesium, calcium, iron, aluminum, silicon. In general, cation and anion, which one has larger radius? Cations have larger radius, is that right? The ionic radius of anions will be larger than cation. They don't necessarily have larger orbitals, but they will repel each other. Second, lithium in one column. In which order?
卢大于钾，大于钠，大于锂。
Rubidium is at the bottom row of the periodic table, so its electron configuration has more shells than lithium, which is at the top row of the periodic table. So rubidium will be larger in radius. Lastly, silicon and potassium, which will be larger in radius. Potassium. Why? They all lose electron, right? Potassium only lose 1 electron. This one lose 4 electron. The more electron you lose, the more electrostatic power the nucleus will exert on its neutron. So they will attract the electron closer to its nucleus. Let's take a look. This figure, if you see letter like this, that means they are not charged. If you see plus minus, that means they are charged, like a chlorine. If it's charged, it expands greatly in radius. Silicon, once it's charged, it loses 4 electrons, so it will be contracted very much. In contrast, it's bulky already. When you lose 1 electron, it's not that bad. It will contract, but it's still larger than silicon. 3D packing. Today, we want to study the 3D structure of mineral. We would use X-ray analysis. That's very convenient for us. By 3D analysis, we know in minerals, negatively charged ions, they are arranged in polyhedra around positively charged metal ions. And they were packed in a repetitive structure with the cations occurring at regular intervals in interstices. So if you look at a piece of mineral, the majority part you would look at is the anion. Cation would be like a small ball inserted into the interstices of the structure. And Pauling's rule tells you what determines the type of polyhedron. This is a coordination number. The blue and the red, which one is anion, which one is cation? Now you have a very good understanding which one should be larger, which one should be smaller. The larger one, they are generally anion. And you see cations is very small, and it's really squeezed into the interstices of the anion. However, with increasing number of anion, you can see that the interstices can gradually accommodate larger cation. Like this one and this one. You see the red ball is much larger than this one. Because in all the polyhedron, the basic rule is the red ball, the cation here, need to be in contact with all the surrounding anion. Pauling, the B group, your assignment is a Nobel Prize. And it's the work done by Linus Pauling. He is a scientist from the last century. And his work in this book, The Nature of the Chemical Bonds, won him the Nobel Prize in chemistry. That's not what I want to tell about him. I once heard a story about him. He was initially an inorganic chemist. That's the reason he works on this. At the end of World War II and after World War II is the era where molecular biology starts to develop. People start to wonder about the chemical structure of biomolecules. The story I heard about Pauline is he was once admitted to the hospital. You can imagine what you would do when you have to lay on the beds in hospital. Nowadays, we will probably use mobile phone, you start to watch soap opera, or maybe play games. What I would imagine I would do. However, what he did is he asked someone to show him his latest data regarding proteins. At that time, he see codes like this. By looking at codes like this, he said, oh, this H and this O, there must be interaction. I think you all know that this is the so-called hydrogen bond. And in order for this H and O to have interaction, the amino acid chain must be folded. That's the discovery of the alpha helix of protein. His work also make people to understand that they are the so-called secondary structure of protein. And this won him a second Nobel Prize. So I was wondering, I don't think I can do that, to look at the data when I'm laying on the hospital bed. The importance of hydrogen bond cannot be overemphasized because this is also the bond that binds nucleic acid together to form the double helix. Okay. Rule 1. Coordination number depends on the relative radii of the cation and the surrounding anions. And now you should have a better understanding regarding cation, which should be small, and anion, which should be large. So you can calculate this. You can also check in literature, it will tell you, okay, this is the radius of this cation and anion. You can calculate this yourself. Fluoride, you can divide the radius of sodium by fluorine. Then you will know the coordination number of fluoride and also quartz by this kind of simple calculation. That's his first rule. The second rule is more complicated, to calculate the bond strength. And the definition is to divide the cation's valence or anion's valence by its coordination number. Here, I shows you the calculation. Fluoride. Calcium is the number here. Fluorine, the number here. So the ratio is 0.85. Therefore, its coordination number 0.85 is this one. It's cubic. For calcium, the valence is 2, divided by its Cn, so its bond strength is 0.25. This mineral, it has only one kind of bond, because this mineral is only made of calcium and fluoride. Therefore, for each fluorine, the bond strength should be also 0.25. You can back calculate what is the number of calcium that fluorine should be bound to. Because for fluorine, you should also follow this equation. Fluorine has a charge of 1, and its bond strength is 0.25 because it shares the same bond strength as calcium. Therefore, this 1 has to divide it by 4 to get this. To make it easier to understand, this is calcium, this is fluorine. For a single unit, you would imagine it to be like this. Calcium is bound to 8 fluorine, and fluorine here should bound to 8 calcium, but here is only bound to 1. So how does that work? For the next unit, there would be no calcium here. For the next, there will be calcium again. For the bottom, no calcium in the interstices, and then calcium here, and no calcium, and then calcium. If you view this fluorine as this fluorine here, you will see that this fluorine is bound to 1, 2, 3, 4 for calcium. It's not that easy to understand because it's 3-dimensional. That's a simple case of fluoride. Here are a few more examples about Pauline's rule 2. Previously, when we talk about fluoride, we have only dual atom, that means 2-atom system. Now we have multi-atom system. Like here we have 3 types of atoms. 3 types, 3 types. Calculate the strength of selected bonds in the following multi-atom minerals. This one will have magnesium oxygen bond, aluminum oxygen bond, and this one will also have calcium oxygen bond and sulfur oxygen bond. This one will also have 2 types of bonds. And here, these two, without star here, they obey Pauline's rule 1. If you apply the number here, you will reach the conclusion that this one has a coordination number of 6. This one is 4. However, these two, they disobey the rule. This happens. In Pauline's rule, it's pretty much an idealized world. And in reality, there are always exceptions. These two disobey Pauline's rule 1. And these are their actual coordination based on X-ray analysis. Now comes to the key point about our assignment. What are the difference between isodesmic, anisodesmic, and mesodesmic? Fluoride has only one type of bond. This is the coordination number, and this is the bond strength. We say this one is isodesmic. All cation anion bonds, they have the same bond strength. Because in this system, there's only one type of bond. Therefore, it's for sure that it's isodesmic. But spinel has 2 types of bond. Based on the coordination number and the valence of the cation, you can calculate its bond strength. Both bond types have bond strength of 0.5. In this mineral, it's a 3-atom system, but they are isodesmic. All cation anion bonds, they have the same bond strength. If, for some reason, this mineral has to decompose means destroy. These bonds and this bond, they will have the same dissociation tendency because their bond strengths are the same. Now we talk about anisodesmic. A specific cation anion bond has bond strength higher than half of the charge of a coordinating anion. In this case, the coordinating anion is oxygen. Oxygen has a charge of -2. The coordination number for this bond is 4. And sulfur has a charge of 6. Therefore, its bond strength is 1.5. 1.5 is already higher than 1, which is half of the charge of oxygen. So it's anisodesmic. If this mineral is to decompose, the sulfate here will not dissociate. If you try to dissolve it in maybe acid, base, or whatever, this bond here, they will not dissociate. They will remain together. But calcium will leave the other atoms. In nature, we see a lot of anisodesmic mineral. For example, calcium carbonate, CaCO3. If you dissolve calcium carbonate in acid, will you obtain calcium, carbon, and oxygen? No. You will obtain calcium and carbonate anion complex because carbonate is anisodesmic. Lastly, mesodesmic. A specific cation anion bond has bond strength exactly half of the charge of a coordinating anion. Again, in this case, oxygen. If you look at the silica here, it has a charge of 4 plus. 4 divided by 4 will be 1. Exactly half of the charge of oxygen. So this mineral is mesodesmic. What does that mean? Bond strength explains the varied nature of different anion and anion complex. Isodesmic minerals, they do not have anion complex. The anion atom bonds with the same strength to all the cations. If they dissociate, they will dissociate at the same opportunity. Anisodesmic minerals tend to have anion complex. The anion atom bonds particularly strong to the central coordinating cation, so they will not dissociate. Mesodesmic minerals have anion complex. Silicate is anion complex, but bonds equally strong to the central coordinating cation, which is silicate in the anion complex, and the additional cation, which is magnesium in this case. The bond strengths are both 1. It explains why silica tetrahedra can polymerize. The oxygen, its bonding strength to silica and to other metal have the same strength. The oxygen, when it wants to balance its charge, if there is external metal out there, then you say, okay, I like you, I want to shake hands with you. However, if at its surrounding there's no other metal, but there are other silica, then it says, okay, I can also shake hands with you. For this oxygen, it's really flexible. I can shake hands with either silica or other metal. That's the reason why silica tetrahedra can easily polymerize, but not the others. Isomorphous substitution. We will come back to this concept several times. Its definition is replacement of cations or anions in a mineral such that no alteration takes place in the form of crystal of that mineral. If you replace a small brick in your body, this will work as long as the skeleton is strong enough. However, if the difference between the original brick and the new brick is too much, the whole skeleton will break. Therefore, if you want this to happen, you want it to happen in the way that the crystal of that mineral remains stable. And what are the conditions that need to be met? Here, replacement depends primarily on ionic size, which means the radius, and valence. We come back to these two important conditions again and again. The extent of substitution is usually limited. If you replace too many bricks in your body, even for each individual step, the change is small. The more you replace your bricks, the more the change it will accumulate, and at some point the whole structure will collapse because you change too much. These are the typical substitution we see in nature. This one and this one, an ion can also be replaced. And this one is also a common scene replacement. I would like to ask, are you aware of any work regarding foraminifera which apply this concept? And I specifically highlight the substitution here.
镁钙铍
Exactly. We know foraminifera is a very commonly used tools in paleoceanography. In paleoceanography, there's a proxy called magnesium-calcium ratio. Scientists measure the proportion of magnesium in foraminifera shell. We know foraminifera shell should be made of calcium carbonate, which is CaCO3. However, because foraminifera shell is a biogenic mineral, and for biogenic mineral, there are also isomorphous substitution. Their substitution also follows the principle here. The ions have to have similar ionic size and same valence. There is a key factor that determines the level of substitution, which is temperature. Applying this principle, paleoceanographers have developed a proxy called the magnesium-calcium ratio in foraminifera shell, and this can be used to reconstruct sea surface temperature in the past. We will come back to this concept again several times. Previously, that was the general introduction about mineral chemistry. Now we will focus specifically on silicates. Silicates represent more than 99% of the minerals found in igneous rock and account for 90% of Earth's crust and mantle. So basically, all the rocks you see, 90% of them is made of silicates. It's also the most diverse mineral class. So we have to have some basic understanding about them. Silica tetrahedra. Draw the distribution of valence shell electrons of a silica tetrahedron, which need to have external metal, which is magnesium in this case, silica, and oxygen here. This is the valence shell electron number 4 for silica and 6 for oxygen. Can you draw the valence shell configuration for the whole things? Magnesium silicate. Not single atom, but the whole molecule, like the way you draw for CO2. Every atoms you see here need to be octet. Does anyone want to provide some correction for this? So this is how it really works. Silicon, 4 valence shell electrons, and oxygen, 6 valence shell electron, and magnesium atom, this is the electron configuration. If it gives away the 2 electron from 3s2, it gives away 1 here, and this magnesium gives away 1 here, then the magnesium here will be 2+, and all of them here, and all of them will be octets. And you might think, why should I learn this? Because after knowing that, you will have a better idea for the next figures. This one is the most simple silicate mineral, olivine. This is its chemical formula. So previously I asked you to draw magnesium 2, but it could be also iron 2. Now you need to know why the structure looks like this. Silicate is tetrahedron. Each tetrahedron here is this. And what are the small balls here? They are external ion, magnesium. Like what I draw here. It's outside the tetrahedron. It's near the tetrahedron and donating its electron to the oxygen to balance the charge. If you understand the octets here, you will understand the structure here. The external metals stick into the interstices of the polyhedron. That's the chemical nature of olivine or orthosilicate. Here I will tell you what is the so-called unit cell, because I told you last time, the definition of unit cell is the minimum unit from which you can repeat in 3-dimensional direction, like in this direction, and in this direction. If you look at the tetrahedron here, go this way, you see another tetrahedron. However, here you see, I mark the unit cell not here, but here. Why? Because this tetrahedron is facing towards the interior of the screen, while this one is facing outward. Therefore, this one cannot be the repetitive unit of this one. So you have to look till the next one where you see, this one is the same, facing out of the screen. So this one and this one, they are repetitive. And the same in this direction. And you need to keep in mind that it's 3-dimensional. So it's not that straightforward to view at the plane. So we talk a little bit more about polymerization. As mentioned above, silica tetrahedra can polymerize. During polymerization, 2 silicate tetrahedra share 1 oxygen. In this case, is there polymerization? No. Here, there is no polymerization because the red ball here, these are oxygen. They don't share oxygen with another tetrahedron. Each tetrahedron is independent. I will show you what kinds of silicates have polymerized. The more oxygen sharing, the fewer additional cation is needed. For each silicate, their charge need to be balanced, so the oxygen can determine whether it wants to shake hands with silicon or it wants to shake hands with another metal. So if the oxygen determines that it wants to shake hands with another silicon, then it doesn't need that much additional cations. Therefore, the chemistry is related to its degree of polymerization. This is the orthosilicate without any polymerization. In the interstices, we put in a lot of metals, so it's metal everywhere. It's metal rich. That's what I mean by polymerization. They shake hands. 2 polyhedrons touch each other. This one is a shared oxygen by this silica. Sorry, you don't see silica here. Silica is in the middle, and this silica. For example, this mineral has a unit cell like this. For sorosilicate, which means paired tetrahedron, they don't really form their own mineral. So they actually form mineral with other polyhedron like this. And these are external metals. Inosilicates is single trend, so you see more oxygen sharing. Like this one. Double trend, you see more oxygen sharing here and there. Like this one. This structure, if you turn it 90 degrees from the side, you will see that it will form layers like this, and for each spot in the interstices, they can stick in different balls. Some space, they can only put in small metal. For other space, they can put in large metal. Cyclosilicate, more sharing. Like this one, beryl is a kind of emerald. Phyllosilicate, you see a sheet. For its junction point, there's an oxygen sharing. Muscovite. This is the form of clay mineral, which we will talk about later. The last one, tectosilicate. It's very complicated. Silicon and oxygen, it has an atomic ratio of 1 to 2. There is no longer external metals. Everything is polymerized. Quartz. In quartz, every oxygen is connected to silicon. Summary, from orthosilicate to tectosilicate, from olivine to quartz. From this kind of formula where we have a lot of external metal to this one where we don't have metal. And their level of polymerization is increasing in this direction. This affects their chemistry. If you are orthosilicate, you can put in iron magnesium. These are highly charged but small size metal. In this direction, you can start to put in sodium, potassium. These are monovalent large cation. And I don't know how many of you have learned Bowen series. These non-polymerized silicates, they are so-called high-temperature mineral, while these highly polymerized silicates, they are low-temperature mineral. High-temperature mineral, they are prone to weathering. And low-temperature mineral, they are weathering resistant. So everything is related to the level of polymerization, reflected in the silicon-oxygen ratio. Clay minerals. In this department, these will be the main minerals that you will work with if you go in the direction of marine geology. Clay minerals are not just silica tetrahedron. They are the combination of silica tetrahedron and aluminum oxide. You can calculate from this table the coordination number of aluminum oxide, and the answer will be this one. This one, the coordination number is 6, but it's an octahedron. So this is silicon tetrahedron, and this is aluminum octahedron. Draw the distribution of valence shell electrons of an aluminum octahedron. Very complicated. This is the valence shell number of aluminum 3, oxygen 6. Aluminum has only 3. It has to distribute these 3 electrons to 6 oxygen because its CN is 6. Oxygen has only 6. Therefore, for each oxygen, there is 1.5 charge missing. 1 here, 0.5 here. We need to balance the 1.5. How do we do that? We now want to balance this guy. So what we do is, first, we have another aluminum oxide here. This aluminum donates its electron in the same way. Then this space is empty. We have another one here. This space is empty. We have another one here. And we have another one here. So you see the regularity here. However, all the oxygens are not balanced. Each of them have 1 electron missing, right? How to balance? We have several options. The first option is to add hydrogens. The second option is to add silicon. This silicon is from silica tetrahedron. This oxygen is shaking hands both with aluminum and silicon. this octahedron and this tetrahedron. They are in contact with each other. And the same way here. Therefore, we have a layer of aluminum oxides, and then we have a layer of silicon tetrahedron. Now you will understand this. This is aluminum oxide. And this is silica tetrahedron. This is also silica tetrahedron. This is the basic unit of clay mineral. The nature of clay mineral is silica tetrahedra and aluminum octahedra form the basic units of layered mineral. Usually, if you see some textbook, they will just show you this. Octahedral sheet, tetrahedral sheet. In reality, they are like this. The fundamental structure of clay minerals, the most abundant mineral in marine sediment. Usually, they are layered. It's one layer here and one layer here. However, do not think of their unit cell as this. Their unit cell should actually include the interlayer space here. Why clay minerals are chemically active is because of this interlayer space. So the actual unit cell is like this, has to include the interlayer. That's how they look like under electron microscope. Let's do the second application of isomorph substitution. In clay mineral, this is the tetrahedral sheet. This is the octahedral sheet. A very common scene isomorph substitution is one silicon is replaced by aluminum. Here, one aluminum is replaced by magnesium. My question is, what is the charge here? And what is the charge here?
Number one, -1. And the second one is -1.
Very good. Both are -1. So here I say one excess negative charge. Therefore, in their surface, there are always negative charge here and there. And this charge will attract cation onto its surface. It's not just metal or proton. It will also absorb nutrients such as ammonia. That's the reason we say clay minerals are chemically reactive, because their surface is charged. Okay, that's for minerals. Starting from next week, we will have 3 weeks of radioactive dating. Usually this is the time when some students think she has to drop because there's too much mathematics. For next time, there will be no distinction between A and B. All of you will have to answer the same question. Return your answer in this Excel file. You don't need to prepare a PPT. Next week, we will talk about isochrone. You can find the example, the whole calculation in textbook. Explain the use of isochrone with the following steps. You first need to explain this equation, how it is derived. It's from the textbook. You can open a new file and you can say, I want to insert some text box. In the text box, you can insert equations. So you can write down your answer here. Write down your answer in a new spreadsheet. Second, work on the spreadsheet of isochrone in this file, here. All the cells in blue should have a number. Isochrone practice. We have isolated 3 different kinds of mineral from 1 meteorite for isochrone determination. That's the case here. That's the mineral 1, 2, and 3. And we know their time 0, number of atoms. I already give you the number of atoms here. You need to tell me what would be the number of atoms after 5% of decay, and so on, and so on. You have to be careful because some of them are stable isotopes, some of them are radioisotope. So this could be misleading because for stable isotope, they don't decay. So you need to know which one is stable, which one is not stable. You should do your calculation. For example, if you think it follows 5% decay, then if I were you, I will calculate like this. Third, use the results in step 2 to plot a figure like this one. Figure 6-4 in the textbook. This line is isochrone. Note, the values in the spreadsheet here, they are not necessarily the same as figure 6-4 because these are numbers assigned by me in order for your practice. But the pattern should be the same. You should be able to draw this kind of line yourself. Then at the end, you need to tell me, in this graph, where do you derive age from this graph? So that's how scientists date meteorite using this kind of graph. If this one sounds very confusing to you at this moment, it's okay. You just go home and read textbook. It has described the whole procedure very clearly, so you can understand the calculation very easily.